All right, hello again. Time for another video. And I'm pretty sure this will be the last video that I ever make as a teacher at Monroe Township High School. So we're in the end of May, middle of May of the year 2023, and this will be the last year for me. But I'm going to try to go out in style here telling you about electricity. So electricity, this is amazing that the human beings figured out how to harness electricity and use it to do all the work that we end up doing. Just a fascinating subject. Don't really think about electricity too much, do we? Until the power goes out. And then we think about it a bunch. But something we take for granted that hasn't been available to human beings for very long. But the starts of it were a long time ago, the start of electricity knowledge for human beings. They didn't call it electricity, and they certainly didn't use it the way we do now. But they really started talking about electricity when way back. Ancient Greeks wrote about it. Wherever there are human beings, they wrote about it. And one of the things they noticed is something that you've noticed, and that's the idea of static electricity. So in particular, there was a lot of writings about amber, which is dried tree sap. And if you're familiar with the Jurassic Park movies, that's the idea, right? An insect with dinosaur DNA got caught in some amber and was preserved for the ages. And then, well, there we go, right? But you know that if you rub some things together, you get charged up. Sometimes when you walk across a carpet and you touch a doorknob and you get a little zap there, these are all examples of static electricity. But the Greeks would do this. They would rub the amber and they would notice that it would build up a little bit of a charge. And that was an interesting phenomenon that they noted and wrote about. And like I said, if you ever did this with a balloon and tried to pick up things after you rubbed the balloon on a sweater or something like that, you've seen that experience. So same kind of thing. They didn't have balloons back then, I don't think, but they used the amber in that way. All right, and yes, of course, socks in the dryer is another way that you're familiar with this, right? When they come out of the dryer and they're sticking together. Okay, and like I said before, sometimes with people, even sometimes when you're built up a charge on yourself, you touch somebody else and you zap them, right? Have you ever had that experience? Probably laugh about that. Not as funny when they zap you, is it? All right, so here's some fun with static electricity, and this is probably done using a Van de Graaff generator, and we have one in class, so maybe we'll try one out. I don't know, we'll see. But yeah, static electricity builds up a charge. Okay, so I've mentioned it a bunch of times, but these are the examples of the static electricity. And sometimes you can, just by being near them, you can give them a charge. And I've already given that example a couple of times over where you walk across a room and touch a door and zap it, or touch a person and zap it. And sometimes you don't even have to be right touching the person. Or if there's two charged objects, just by being close to each other, they can become charged up. So there you go. All right, and these charged objects, you've heard this saying so many times in life probably, but it probably starts with physics, and that is the idea that, and it applies to magnets too, right? That opposites attract and similar things repel. So objects can be attract other objects, and they can also repel other objects as well. And I've already mentioned what the rule is going to be. But that's why a balloon can pick up pieces of paper. The balloon is charged and it can pick up neutral things, and vice versa. All right, so they're either positive or negative, and do you know who came up with that way of talking about charges, positive or negative? They could have called it anything, up and down, right and left, blue and green. They called it, it was Ben Franklin who decided, let's call it positive and negative. And Ben Franklin was famous for being on the $100 bill, but also for doing experiments with electricity. So you may be familiar with that idea of going out in a lightning storm. That was actually a pretty dangerous move on his part there, becoming part of the grounding process. All right, so finish this famous saying. Opposite charges attract and similar charges repel. So two positive charges will repel each other, two negative charges will repel each other, and a positive and a negative will be attracted to each other. Okay, so if an object is charged up, it can lose its charge by being connected to the ground. And that's how they deal with a lot of electricity in the house. Like if lightning hits your house, there's probably a lightning rod. And Franklin was involved in inventing that as well, that would bring the charge to the ground and not have it be dangerous to the house or the people in the house. So by grounding, you can do that. And that's the deal with lightning. There's a big charge up in the sky. All right. An electroscope is a device that'll help you figure out a static charge. This was figured out a long time ago. So they do it with touch, and they'll touch something on this metal piece, and we might mess around with those in class too. And the little things in the middle, if the charges that have been applied to it are the same, then they're going to move farther and farther apart because they're repelled by each other. And if they are different, you'll see those two pieces in the middle come together. All right, so like I said, in ancient Greece, they figured this stuff out, and we now call the negative charges electrons. And we have the idea that all this electrical phenomenon is due to the movement of the electrons. And the ancient Greeks had a word for electron, and do you know what electron means in ancient Greece? I didn't know either until I taught this class, but it means amber. So as a nod to those early studies in static electricity with amber, the scientists of recent times have decided to call them electrons. And all of this electrical phenomenon is due to the movement of the electrons. That's our understanding of it now. That's a good way of talking about it. Okay. So if there is charge to an object, there can be a lot of charge and there can be a little bit of charge, right? So there is a measurement for these charge, and they're measured in coulombs. So these are some of the last units that we'll be talking about. But charge is measured in coulombs, and an electron has a very small charge to the negative 19th, 1.6 times 10 to the negative 19th coulombs. So by itself, one electron isn't going to really do too much. But when you get those electrons flowing, as the human beings have figured out how to do, you can get a lot of work done. All right, so Coulomb's law is interesting to me because it's set up very much like the inverse square law that we saw with gravity. So remember, with gravitational attraction, we had capital G, the universal gravitation constant, and K we have as Coulomb's constant. And that means you can figure out the force in newtons for two charges, Q1 and Q2, are the symbols for each of the charges, like we used mass 1 and mass 2 with universal gravitation, and R is the same thing, the distance between the two of them. So F is going to be the force of attraction, or repulsion, measured in newtons. K is a constant, 9 times 10 to the 9th. And Q1 is charge number 1 and Q2 is charge number 2. R is the distance between the two of them, and that'll be measured in meters. So the charges, of course, will be measured in coulombs. And by doing this, the force will end up being in newtons. So let's take an example of that. Let's say you have two 5 Coulomb charges. They're 1.5 meters apart. What is the force between them? Maybe you want to pause the video now. Give it a try for yourself. Identify the information. Plug it in. See if you can get the correct answer. And then come back and we'll see how you did. All right. Well, welcome back if you decided to take the break. And did you get this answer? 1 times 10 to the 11th newtons. That's the answer for this one. You might remember the gravitational attraction was very small. So electrical attractions with that inverse square law again are very much stronger than gravitational attractions. So a lot of work can be done on electricity. You got to be careful, because if it does the work on you, you can get zapped pretty good. All right, is this one positive, or it's a positive force? Is this an attraction or a repulsion? What do you think about that? Right? You had two positive charges multiplied by each other, so you got a positive answer. Well, two positive charges will repel. And if they were two negative charges, they would also repel, and the answer would be positive. So a positive force is a repulsion, and a negative force is an attraction. I remember when I first learned this, that was a little counterintuitive, right? I would have thought that negative would have been a repulsion, but you can see with the math why this is not the case. All right, so here's the solution. If you're having some troubles with it, I'll help you through it. We identify the information as we always do, And having identified the information, we will plug the numbers into the equation. And it's going to look something like this. And again, getting the calculator to do what you want can be tricky, but that's how you should come up with the 1 times 10 to the 11th newtons. Coulomb's law. You'll have some chances to practice that a little bit more as we wrap up this school year. 2023. All right, so lots of uses for electricity. And we don't want all the electrons flowing all over the place. Like I said, they could do a lot of work. They could zap you pretty good. So we insulate our electricity, and insulators are objects that cut down on the flow of electrons. That's why you're going to wrap your cords in rubber and that kind of thing to keep them. And conductors, like a wire, metal, will easily allow the flow of electricity. So insulators cut down on the flow, inhibit it, or cut down on it, and conductors allow the flow of electricity. All right, so buildup of electric charge, if you have it, it is potential energy. It's ready to do some work for you. So voltage or electrical potential is the buildup. So that's what they do. They build up a bunch of negative charges on one side and positive charges on the other. If you ever seen a battery, you know it has a positive and a negative sign. So voltage is the amount of work that you do per charge, how much work is done per charge. And that's it. When you build up a lot of voltage and then you let those electrons go, that potential energy becomes the kinetic energy of the electrons flowing, and then the human beings, and I consider myself one of us, have figured out how to attach that to all kinds of things to do all kinds of work for us. And this is when we get the electric current flowing through an outlet. And that's pretty good. Or through a battery or through a wire. But electric current is the flow of electrons. Make no mistake about it. Now you know. We don't think about these things too often, right? Because it's just there for us. All right, current is a measurement of the flow, and that's amperes. So amperes is the unit for current. Yeah, we got some new symbols to get together, right? Symbols and units. All right, so 1 ampere is 1 coulomb per second. In a way, this is watching the river flow. You could think of the flow of electrons as like a river coming by. And here you would be measuring how many charges, coulombs of charge are coming by per second. So there you go. All right, an ammeter is a device that'll measure the current. So if you're ever working on electricity, or if you have an electrician come in, or maybe you'll become an electrician. That's a great occupation. Boy, people who know about electricity are still in demand. Amazing. All right, so an ammeter is a device that measures the current, and the current will run through all kinds of appliances. So I just picked a picture of some stuff here. So some irons, and I mean, just how many electrical appliances can you think of? There's so many of them. Popcorn poppers, of course. But I'll tell you what, the inventions of the human beings that we've used with our amazing mind are, to me, no less incredible than our amazing minds. And this is what our brain does too. Our brain, everything that we sort out in our brain is because of electrical signals that are being sent to the brain. So it's this ability to sort through these electrical signals. And I had talked about that with sound before, that we can sort out all these sounds. But all our thought processes are these movements, and that we can sort out all this information and process all this information and have this all long-term and short-term memory. But there's an example of electricity moving through a something or other. Human being. And you all have an amazing thought process that's completely unique to you. It's been great to know you. All right, an electric circuit is going to supply the steady current, so you can rely on the current, and voltage is what drives the current around a circuit, and that makes sense, right? That's the driving force of it. And here's an example of like a battery, that things would be flowing from negative to positive around the battery, and that's how it works. We figured this out a while ago, the human beings. A voltmeter will measure the voltage, so you want to see what's going on with your voltmeter. And here's meant to be a funny picture about some people trying to figure out the lighting in the house. So there you go, or the electrical outlets in the house. But we are so involved with this electricity. So here's a circuit breaker box. And the idea of a circuit breaker is, sometimes you're going to get a current that's too much. Your wiring can't handle it. So a circuit breaker is something that's going to trip, meaning that it'll block out the electrons from flowing. It'll stop the flow of electrons. It'll open up that circuit, and it'll sense that the current is getting too high, and you'll trip the breaker. You might have been involved in some of that kind of stuff in the past. This is a more modern approach, the circuit breakers are, than what they used to do. But if you're ever doing work on your electricity at home, same deal. You want to cut the circuit breaker so there's no electricity going to that outlet that could cause you some problems. All right, and so they're going to break if, like I said there before, if you get to too dangerous amount of the current. All right, fuses they were done a little bit before that. Like a circuit breaker, you can just turn it back again, But fuses were a little piece of metal that would melt before the circuitry in the house or, that you're in your circuit would melt. So the fuses would melt first if your current was getting a little bit too high. And that way you protected the other ones, because as soon as the fuse melted, the fuse was part of the circuit. They put it in the circuit, and when it melted, it opened up the circuit. A closed circuit is one where the electrons can flow, but once the fuses were burnt, then the electrons couldn't flow past that point anymore, and that would save the rest of the wiring. Very clever, very clever. And of course, these ideas came out from people who did overrun this stuff, and house fires would have been involved. So this was a nice discovery after the discovery of electricity. Very interesting thought process. So here's some old fuses. I lived in a house there in Jamesburg, New Jersey. That's the longest I ever lived anywhere. And we had two setups. We had a setup upstairs with fuses, and we had a circuit breaker in the basement. But it was an older house, so they had made those transformations. Okay, and that's what the fuses look like up close. You screw them out and put them back in again. Some of you may have seen them. They'll probably be going out of style, though, right? And that's what the fuses look like. They still use them in cars, too. So sometimes you might have to replace a fuse in your car if something goes. All right, and electric outlets. We're so prevalent with them. And I remember in my house, too, we would trip the circuit breakers and do that from time to time because, it wasn't built for the amount of electricity that we utilize today. So we're very prominent and prevalent, I should say, in our use of electricity. Our use of electricity is very prevalent in today's society and probably will be for some time. All right, so there's resistance involved in these things. And that's sometimes if you touch things that have been had light going through them or electricity going through them, you feel they're hot to the touch, like the old incandescent light bulbs. That's because of resistance. Resistance is measured in ohms. It's kind of like friction is, right? It's the resistance of the motion of the current. So resistance is measured in ohms. So another symbol and a letter to get used to. Ohm's law, and you can think of it like this, is I is equal to V over R. I is the letter for current, and voltage is the V is the symbol, and V is the unit for voltage, and resistance, the letter is R. So I is equal to VR makes sense, right? The V is on the top, so the bigger the voltage, the more current. And on the bottom is the resistance, because the bigger the resistance, the less the current is going to be. But Ohm's law can be shuffled around lots of different ways. And I'm going to use the one on the right-hand side for you. The V is equal to IR. I think that's the easier way of using it. So we'll do it that way. It's all the same thing. All right, so let's do an example. Here we have a light attached to a household circuit. Voltage is 110, like a lot of circuits are in the United States. And what is the resistance in the lamp if the current is 2 amps? So you can try that and come back. Pause the video if you want. All right, are you back again after pausing? All right, first of all, you would identify the information. We got the voltage. V for voltage is 110 volts. I for current is 2 amps. And R is what we're looking for. So if we start out with this form of Ohm's law, V is equal to IR, Then the voltage is 110, the current is 2, and we will divide off the 2 to find the resistance, which in this case is 55 ohms. How did you do? All right, hope it worked out for you. All right, so power is the rate at doing work. We know this before when we discussed power and energy. So power is the work divided by the time, right? The work in joules divided by the time. So power in a electrical sense is current multiplied by voltage. You know, if you remember, current is the charge per second, and voltage is the amount of work per charge. So it really comes down to work per second again. So power is equal to current multiplied by voltage. We'll use that equation back in class. And power is measured in watts. You've probably heard of that before, with light bulbs probably, right, or something else. How many watts of power? Now, watts is pretty small, so power is measured in watts when you multiply current multiplied by voltage. But a lot of times the human beings like to use kilowatts because kilowatts are 1,000 watts, and that's a more useful unit to talk about. But like I said, you might remember the incandescent light bulb, or light bulbs, LED light bulbs as well. They talk about their wattage, how much power they put out. All right, this should make sense too, right? If power is equal to work divided by time, then power multiplied by time is going to be the amount of electrical energy or work that you do. And that's how they charge you. So there's nothing realer in the world than money, and electricity comes at a cost. So the way they bill you is by power, kilowatts, and seconds is a little bit short for the amount we use our appliances. So they bill you in kilowatt hours. Power multiplied by time tells you how much electrical energy you used, and that tells you how much they're going to charge you for. So get ready for the real world when you too may get to pay for electrical energy. All right. So here's a circuit. They got all kinds of circuits. The human beings have figured out all kinds of great stuff with electricity. So I'll close with that. And again, I'm closing with, I think, my last video. I can't even imagine. I've lost count of how many videos. I mean, so many videos here in my time at Monroe Township High School. And this here's my last, as I'm getting ready to go on to new chapters in my life. But I must say that I've had the best job in the world, and every one of you is part of that. So thanks for being you, and good luck in your futures, and good luck with me in my future too. All right, good people. See you back in class a couple more times.